We're going to look now at natural logs. So first thing is then a is a special number in maths. You don't have to know too much about it. It's to do with exponentials, but it's like pi. It's a special number. It's 2.71828 and so on. But it's associated then with logs. So log to the base e of x is written as ln of x. So you might have seen the wee ln button on your calculator. Maybe some people even thought it's 1n, but that just means log to the base e. And the inverse of ln x is e to the power of x. Okay, and again, on your calculator above the ln button, you'll see the wee e button. Okay, now these logs follow all the same rules as logs to the base 10, logs to the base 2, anything like that. It's just a special base now, and you'll see it written as ln x, the same way as log 10 is seen as special and is written as log. Log to the base e is written as ln x, and again, all the same rules apply. So you'll get all the same type of questions. So we can have a solve question. So solve part A then, e to the power of x equals 3. So you take log. So if you had something like 2 to the power of x equals 3, you would take log to the base 10. But when we've got an e, we'll take natural log. So ln e to the x equals ln 3. We'll bring the x down the same way as we would if we did this type of question. Now you know that log of 10 to the base 10 is 1. Log of anything to the same base is 1. So if ln e really means log to the base e of e, that means that is 1. So we can write x equals ln 3. Now you can find out the value of that in your calculator, or a question might just ask you to give the exact value or leave it in terms of log. B then, e to the power of 2x plus 3 equals 4. Again, we're going to take natural logs. And again, the format of the question is exactly the same as if this was log to the base 10. So we'll bring our 2x plus 3 down. And then ln e is just 1. Bring the plus 3 across and it becomes a minus 3. And then we would divide the whole thing by 2. This is how you would leave it if it was an exact value. If it was asking for 3 significant figures, you would put it into your calculator and you get minus 0.807. Part C, ln x equals 4. So remember, ln means log to the base e of x. So we know we can write that using the same rules of logs that we've already looked at, as x equals e to the power of 4. Now sometimes again you'll be asked to give it as an exact value, which means you just leave it as e to the power of 4. Or if you're asked to give it to 3 significant figures, you put that into your calculator and get 54.6. Or D then, 2 ln x plus 1 equals 5. So the first thing we're going to do is take that plus 1 across. So we'll get 4, and I'm going to divide by 2 and get ln x equals 2. So we can say x equals e squared. And again, if it tells you to leave it as an exact value, leave it as e squared. If it tells you to do it to 3 significant figures, put it into your calculator and we get 7.39. Part A, ln of 2x minus 5 equals 8. So we can write 2x minus 5 equals e to the power of 8. So 2x equals e to the power of 8 plus 5. So x would be e to the power of 8 plus 5 all over 2. And again, that's your exact value. Or 1490 to 3 significant figures. f, then ln x plus ln x minus 3 equals 0. So again, you can see you're getting the same type of questions as you got in the normal logs questions. It's just a natural log. I'm going to combine these then, so it's a plus, so that means we're multiplying. Okay, all the same log rules apply, so we can write x and x minus 3 equals e to the power 0. So that's anything, remember, to the power 0 is 1. Multiply out the brackets, I get x squared minus 3x, and I'm bringing the 1 across. Minus 1 equals 0. That's a quadratic. If you use the formula to solve it, you'll get 3 plus or minus root 13 all over 2. E to the 4x equals 5. Again, take natural logs. Both sides, bring the 4x down. That means 4x equals ln 5. So x is a quarter of ln 5. H, then e to the x plus e to the minus x equals 2. So I would write that as e to the x plus 1 over e to the x equals 2, and then multiply across by e to the x. So that means I'd have e to the x times e to the x, which is e to the x squared, plus 1 equals 2 e to the x. So this is one of those hidden quadratics. So if we bring everything to the left-hand side, and we let e to the x equal y, that means we'd get y squared minus 2y plus 1 equals 0. So we're going to solve that. You can factorize that to give you y minus 1 upon y minus 1 equals 0. So y is 1. We know that y is e to the power of x, so we have e to the power of x equals 1, so the only value x could be there is 0. And I then 24 minus e to the power minus 2x equals 10. Okay, so I'm going to bring the 10 across to the left-hand side and bring the e across, so we'll get rid of the minus in front of it, so we'll have 14 equals e to the minus 2x. Now I'm going to take the natural logs of both sides. I'm going to bring the minus 2x down, ln e is 1, so minus 2x equals ln 14. So x is minus a half ln 14. Okay, so now you will see more of these type of questions in past papers and stuff with natural logs than you would with the other log questions. I'll try and put some kind of scenario around it. So the price of a used car can be represented by P equals 16,000 e to the minus t over 10, where P is the price and T is your time in years, okay? So calculate the new price. Well, that means, well, what is it whenever T is 0? So P equals 16,000 by e to the power of 0. We know that that's 1, so P equals 16,000. For B then, the value at 5 years, so T equals 5. So the price is 16,000 by e to the power of minus 5 over 10. So 5 over 10 is a half, so that's e to the power of minus a half. So on our calculator, we get £9,704.49. And I would say, well, it's a price of a car. You're not going to pay £9,704.49p. £9,700 seems more reasonable. And part C then, calculate how long it will take for the price to be halved. So we had found out in part A that the price started at 16,000. So we want the price now to go to 8,000. So 8,000 equals 16,000 e to the minus t over 10. Bring the 16,000 across and divide, we get a half. take logs of both sides. So log of a half equals the log of a to the minus t over 10. Bring your minus t over 10 down, and then we know that that's 1. So minus t over 10 equals ln a half. So minus t is 10 ln a half. So t is minus that. And that turns out to be 6.93 years. And question 3 then. The number of elephants in a herd can be represented by the equation n equals 150 minus 80 e to the power of minus t over 40, where n equals the number of elephants in the herd and t is the time in years after 2003. So first of all, calculate the number in the herd in 2003. So that means when t is 0. So we're no years after 2003. So n is 150 minus be 80 e to the power of 0. So that's 150 minus 80, which gives us 70 elephants. Part B, the number of elephants in the herd in 2007. So that's when t is 4. So 150 minus 80 e to the power of minus 4 over 40. So that's minus a tenth. So on our calculator, we'll get 77.6. So it's elephants we're talking about, so I'm going to say there's 78 elephants. And part C then, the year the population will grow to above 100. So let's say, well, when will it equal 100? So 100 equals 150 minus 80 times e to the power of minus t over 40. So I'm going to bring this part across and we get 80 e to the minus t over 40 equals 50. Brought the 100 across, 150 take away 100 gives us 50. Then divide across by 80 and we'll get 0.625, and now take natural logs at both sides. Bring down the minus t over 40. So minus t is 40 times ln of 0.625, so t is minus that. And we get that t is 18.8 years. So that's when it's equal to 100. We want the year that it'll go above 100. So we'll say that it'll take 19 years from 2003. So that means our answer is 2022. So remember, it asked for a year, so your answer should be a year.